In this video, we are going to look at how to calculate the number of time periods in our time value of money equations. There is a way to quickly estimate the amount of time it would take an investment to double, and we call this our rule of 72. It's just an estimate that will give us the amount of time any investment would take to double. The equation is relatively straightforward, and we simply take the number 72 and divide it by our annual rate of return. An important detail to this equation is that when you divide by your annual rate of return, you only use the whole number for the percentage, not as a decimal point. So for example, if you were going to divide it by 12%, you would simply take 72 and divide it by the number 12, not 0.12. And we do that to get our approximate number of years to double an investment, whether that's $1 to $2, 100 to 200, or $1 million to $2 million. And so again, just to recap, we're only going to use the number for the percentage. We're going to take the number, drop the percent sign for our calculations. So for example, if you wanted to know approximately how long it would take an investment to double, maybe $2 million to $4 million, if it earned 5.5%, we would simply take our 72 and divide it by 5.5, or it would take approximately 13.09 years to double. If we look at another example, how long would it take approximately for an investment to double if it earned 11.75% per year? Again, we simply take 72 and divide it by 11.75. We do not use it as a decimal point, and that gives us 6.13 years. So in this case, an investment that earned 11.75% would take approximately 6.13 years to double. And that method offers some advantages in that it's relatively simple, but it's not exact, and we want to be more exact than that when we calculate our number of time periods. In order to do that, we are going to use some of the properties of a natural log. In particular, we can use it to solve for exponents, and we are going to use the power rule for the natural log. The power rule of natural log says that if we have some equation, in this case x raised to the y power, and we take the natural log of it, once we take the natural log of it, we can use that exponent and bring it down in front of the other number, in this case to make it equal to y times the natural log of x. So to be sure, the natural log of x raised to the y power is equal to y times the natural log of x. We can use that property for a natural log when we calculate or solve for our number of time periods. So in this case, our x would be equal to 1 plus r, and our y would be t. And so if we take the natural log of the quantity 1 plus r to the t, we can simply bring that t down in front to where we have t times the natural log of the quantity 1 plus r. So, if we use our future value function, for example, and the natural log, we can solve for the number of time periods. On the top right of the slide, you'll notice that we have the natural log property with respect to t. Again, we have our future value function, where future value is equal to present value times the quantity of 1 plus r to the t. If we divide both sides by PV, we get that equation. And now we're going to try to deal with that exponent of t. And in this case, what we've done is we've taken the natural log of both sides. So on the left-hand side, we have the natural log of the quantity of FV over PV is equal to, and now we've taken the exponent and brought it in front, is equal to t times the natural log of the quantity of 1 plus r. And if we solve for t, we get that t is equal to the natural log of the quantity FV over PV divided by the natural log of the quantity of 1 plus r. And I understand it may look a little daunting, but fortunately a lot of our calculators will have a natural log function that makes this process a lot easier. And so before we looked at the rule of 72 and we got an approximate value on how long something would double, but now we want to calculate exactly how long it would double. And in order to do that, we need to first assume how much present value we have. In this case, I just chose $100 because it's an easy number to deal with. It could have been $1. And then our future value is just going to be twice that amount. So in this case, if our present value was $100, then our future value would be $200. It isn't important what numbers you use here, just as long as the future value is twice the present value in this example. Here we see our equation for t again, and in this case, our number of years to double, approximately using the rule of 72, was 13.09, and we'll see exactly how long it takes. So this is our equation, right? $200 is our future value, equals $100 or our present value times the quantity of 1 plus r to the t. We divide both sides by $100. We take the natural log of both sides in order to make that equation equal, and we bring our t down to the front. So we get the natural log of the quantity of $200 divided by $100 is equal to t times the natural log of 1.055. We solve for t. And we find out that it actually takes 12.946 years to double. So our rule of 72 gave us a different number, and the actual number takes a little bit less time. Now we'll look at another example. Assume you invested $1,000 and your investments are now worth $3,750. If you earned an annual rate of 8.5% and had quarterly compounding, how many years were you invested? And so first we're going to set up our future value equation, where our future value is equal to $3,750 and our present value is $1,000. Our R is going to be 8.5% divided by 4. And in this case, we need to take our number of years and multiply it by 4 in order to solve for our t. So here we divide both sides by our $1,000 or our present value. We take the natural log of both sides, and that allows us to bring our exponent down on the right-hand side. And we eventually get that 4t is equal to 1.321756 divided by 0.021027. And our t is going to be equal to 15.7147, and that is the number of years. The number 62.858837, that is the number of quarters that it takes for us to reach that value. And so at the end of the equation, we need to make sure we adjust for that quarterly again. Because we solved for quarters, we need to change that to years because that's what the problem asked for. And so that's why we divided by 4 to get 15.7147 years. So again, when we solve for our number of time periods, we need to make sure that we adjust for any compounding. In most cases, it simply means that when we solve for our t, we need to make the adjustment for whether our values are going to be compounded quarterly or semi-annually or monthly. So in this case, if we would have had a monthly compounding, what we could have done is just wait until the end to solve for our t and then get a number of months and divide that by 12, and that would have given us the number of months.